Hey, it's Brainmuffin back with a bit of a vlogging braincast, if you will. So I came across an article today that talked about scientists possibly finding a pattern to the seemingly random distribution of prime numbers, which I think is very interesting. Now, this article, when we'll get into it, it does get into what a prime number is, and I'm not going to bore the audience with that, but we're just very quickly. Prime numbers are odd. With the exception of 2, and there's some question as to whether 2 are really a prime number, but basically it's a number that's not divisible by 2 other than 2. So 2, 3, 5, 7, 11, 13, 17, 19, 23, I think, 29, 31. So you get an idea. So let's get into it. So, and basically it's with crystals and patterns. It's very interesting. So this comes to us from motherboard.vice.com. So it goes into often the building blocks of mathematics. Prime numbers have fascinated mathematicians for centuries due to their highly unpredictable, seemingly random nature. And if you think about it, if you take 2 and you add 1, you get another one, right? You get 3. If you add 2 to 3, you get 5. And if you add 2 to 5, you get 7. You think, oh yeah, no, because then you get to 9, and that's not a prime number. But 11 is. So there you're doubling what you previously added, or your last 2 adds, and think 4. Okay, great. Now where's the next one? Well, the next one's 17. So you go from, because 12 is, or 13 rather. I forgot about that one. So now you're adding 2 again, and then you're adding 4. And then you go from 17, well, if you add 2, you get 19. But if you add 2 to that, you get 21, which is not a prime number. Then it's 23. And so it feels like there's patterns, but there isn't. So it's fascinating. So, however, a team of researchers at Princeton University have recently discovered a strange pattern in the prime chaos. Their novel modeling techniques reveal a surprisingly similarity between primes and certain natural occurring crystalline materials, a similarity that can carry significant implications for physics and material science. Prime numbers also play a part in encryption. Usually you use very large prime numbers, so finding one, and that's part of theoretical mathematics. If given a prime n, no matter how big it is, what is the probability? Because n plus 1, because it's an odd number, it's going to be turned even, and it's no longer a prime number. But what is the probability that n plus 2 is also prime? And that's you can make a lot of money following that. So here they go into what prime numbers, which I've already just discussed. So let's get to the meat and potatoes, as it were. A productive hunch. Chemists and physicists typically study the structure of a material by firing X-rays at a sample and observing how the rays scatter off the atoms within it. This process is known as X-ray diffraction, where different materials produce different patterns depending on how symmetrically their atoms are arranged. So crystals have very different structures. These are solid, so this is glass and quartz, and there's a lot of crystalline structures. Many of them are microscopic. Sand is a very crystalline structure, but you can't really hold it up very easily and see how it's composed. A liquid whose atoms are jumbled and moving, and this would also be true of gas, will scatter the X-rays all over the place. Now, and obviously, the more excited the liquid, the more they're going to scatter, and the more random they're going to appear. Whereas a crystal's rigid lattice of atoms, such as in salt or diamond, so there you go, there's 2 good ones, will diffract them in a more orderly manner. The way that this is written, and this is hard for me to read, because I wouldn't write it that way, a manner due to their repetitive internal structure. Additionally, rare materials known as quasicrystals create similar diffraction patterns without having a repeating atomic structure. So that's very interesting. What it probably means is these, I don't really know a whole lot about quasicrystals, but I'm going to guess that they show these patterns probably based on the atomic structures that are there and what they're composed of, and how these, they're almost, I guess, are they molecules? Molecules are a collection of atoms, right? So it depends, something that as a denser molecule is going to scatter differently than one that's less dense, where maybe the X-rays go through it. In both crystals and quasicrystals, the X-rays typically form a pattern of periodic bright spots known as Bragg peaks, as the rays constructively interfere with each other over fixed intervals. Last year, theoretical chemist and Princeton professor Salvatore I guess that's Torquato, had a hunch. What if prime numbers were modeled as atomic-like particles? Would they create a pattern too? Together with his student, of course, we're going to have to get, all these 4 names. Ji Zhang and number theorist Matthew de Courcy, Ireland. I don't know. I wanted to say that that's French, but Ireland isn't. Torquato computationally represented the primes of a one-dimensional string of atoms and scattered light off them. So that would be 2, 3, 5, 7, so one dimension. So not so along a single axis, say along the X number line, or like just the number line. The result, published in Journal of Statistical Mechanics Theory and Experiment, that sounds like a great read, last week, was astonishing. Not only did they create a quasi-crystal-like interface pattern, but it was a type of fractal pattern that has never been seen before. Torquato told Quanta magazine that this implies prime numbers are a completely new category of structures when considered as a physical system. Now, that's a very interesting statement, because I have long thought of the number structure, sets of numbers. I've always and numbers have always fascinated me, and math has always fascinated me. And when I learned years ago in discrete math that your set of integers is infinitely smaller than your set of real numbers, between 0 and 1 there's an infinite set of real numbers, just as if between 0 and infinity there's an infinite set of integers, but all of those integer numbers are actually occur between 0 and 1 when you put them all to the right of the decimal place, and then they repeat between 1 and 2 and 2 and 3 and so on. So there are different orders of infinity, basically. And anyway, so curiously, this uniquely fractal pattern only appears over significantly long stretches of the number line. Over shorter stretches, so this is why, it's a 2, you add 2, no, you add 4, then we add 2, then we add 2, and then the pattern jumps. Over shorter stretches, the pattern fails to emerge. Known as hyperuniformity, so large over the greater existence, this is a rare property that only a few materials and systems in nature demonstrate, such as the arrangement of color-detecting cone cells in birds. And now I sound better because I moved more to the center of my microphone. One of these days I'm going to figure out how this thing works, and I'm going to sound good all the time. I know it's a side note, but at least I'm not talking about pies. So let's see if I can do this in my, guys, right here we have certain emulsions and quasicrystals, the large-scale structures of the universe, as it turns out, prime numbers. Well, this same finding are not groundbreaking for number theory. I think that's a bit premature, because there really hadn't been any concept of a real pattern. It was an anti-pattern almost. As most of the relative mathematicians have seen before in other forms, they may prove useful in a new research known as a periodic order, the study of non-repeating patterns. Much of the experiment surrounding the paper's excitement, stems from its unique intersection between the physical and more abstract mathematical realms. Henry Cohn, a principal researcher at Microsoft Research, who was not involved with the study, told Princeton, "It's a beautiful new perspective on this information, and it opens up new connections with materials science and scattering theory." And see, again, I think this gets to numerology, and there's concepts of the universe. There's, again, even in the appearance of what appears to be random, there's still an order and a law at play. Additionally, the paper claims to have produced an algorithm which enables one to predict primes with high accuracy. Now, that's very encouraging. While the usefulness of such a tool is not yet known, I told you at the beginning, who is writing? See, this is the problem. You have these adults who write this who don't know crap about crap. It doesn't matter if we're talking about Star Wars or whatever else. Again, we come across something that's just stupid. It makes another step towards conclusively solving the enigma of prime numbers. Encryption is just one of many areas. There's also been some thing with prime numbers and protein folding and RNA and DNA and mutational rates and all kinds of other stuff. I digress. But anyway, it was a decent article. Something that's not Star Wars and not depressing and not how Doctor Who is being destroyed or any other SJW nonsense. Now, at some point, I'm sure someone will complain that this article made no mention of the declared non-primes that have declared themselves prime, and primes who have declared themselves non-primes, since this is a non-binary system. And the concept of a prime number is just a social construct, and so it can't be applied to a number without its consent. That'll be the next digression of stupidity, most likely. And so I love it. The advertisements are whacked because of my plugin on the browser. All right, so there you go. Thanks for stopping by. This is something a little bit different, a little bit more in the science realm, but in math is my math, I'm a bit of a math nerd, and I've been promising for a long time we're going to do calculus and other stuff, and we'll get to that. So I don't know, this is like the brain vlog, I think, and I want to do more of these as I find more articles to share, and hopefully next time I won't be so long-winded and boring. All right, thank you very much, and we'll see you. Goodbye.